This is a video about how we design things. It's a video about priorities, and how we sacrifice things like energy efficiency for the sake of convenience, and vice versa, and why we should put meaningful consideration towards those sacrifices we make and the priorities they enable. As I'm sure you've gathered from the title, we're talking about freezers. Well, actually refrigeration more broadly, but to make the point I'd like to make with this video, we're going to talk about one of these little beauties. This is a perfectly ordinary chest freezer. It's a box with a lid that keeps things very cold. Now, on its surface, this isn't remarkable at all. But if you know anything about chest freezers, you'll know that they use an almost comically small amount of energy to do their thing. And the reason that's possible is because of their efficiency-first design. To start, let's consider what refrigerators and freezers do. Their most basic task is to move heat energy from inside themselves to the outside world. They're in a constant battle with ambient energy. If you want there to be a space that's colder than its surroundings, well, you're going to discover pretty quick that all the energy around that space would really like to spread out, and so it will eventually find its way inside your cold box. Entropy's a pernicious little monster. The miracle of refrigeration has allowed us to fight that impulse of nature. Using nothing more than a compressor, a couple of heat exchangers, a metering device, and specific chemicals, we can say, "Screw you, entropy!" and reverse the natural order of things. How? Well, we don't need to get into the specifics here, and I know I've teased a video on refrigeration multiple times, and I'm doing that yet again. I really just want to find or come up with a better demo for you all, so sorry. Suffice it to say, we take a chemical and use the properties of latent heat to move energy around on our command. By manipulating the pressure the chemical is under, we can change its boiling point, and by controlling where and when it boils and recondenses, we can exploit the latent heat of vaporization. The miracle of refrigeration is that the energy we put into the system through mechanical compression of the refrigerant is only a fraction of the energy that the refrigerant is able to move. In other words, say you expend 100 watts of electrical energy in a compressor of a refrigeration system. That system is now able to move the equivalent of 400 watts of heat energy, or possibly even more. It's really neat, and using refrigeration in reverse to concentrate heat energy rather than to disperse it, we usually call this device a heat pump, will likely be instrumental in our fight against climate change. All we need is refrigerants with a small global warming potential, which luckily are starting to see commercial deployment, such as R1234YF. Anyway, setting aside the mechanical bits that make the heat go out, what every single piece of refrigeration equipment in this world wants to do is create a thermal barrier between its insides and the outside world. Because no matter how miraculously efficient your heat pump design may be, unless you can slow the spread of energy from high concentration to low concentration, the refrigeration device will need to run a lot, and so it will use a lot of energy. I'm sure you've used one of these before. It's a cooler. The walls of the cooler are well insulated, which slows the progress of heat energy trying to enter it. And that lets you keep things that are inside it colder for longer. See, the thing you have to keep in mind is that things that are cold are actually devoid of energy. I'm going to put this down. When you feel a cold can of your favorite beverage from the fridge, the reason it seems cold to you is that it's sucking the heat energy out of your hand, and our bodies interpret that sudden loss of energy as a sensation of cold. Really, your hand is warming up the can. The can sort of steals the energy that's in your hand simply because energy wants to spread out and equalize. Aluminum is a pretty good conductor of heat, which makes it feel particularly cold. If you simply take a bunch of cold cans and put them in a grocery bag, well, the heat energy in the room, or the environment more broadly, will find its way into the cans relatively unimpeded. Air isn't super great at heat transfer, but it will happen. However, if you take those cans and put them in a cooler and close the lid, well, now the cooler has become a barrier. The heat energy around the cooler has a hard time getting through its insulated walls, so the cans stay colder longer. Fill this up with ice, and now you've got a larger thermal mass, which means the effect of the heat energy entering the cooler causes a smaller temperature rise since there's more mass to heat up. The upshot of which is that things stay colder even more longer. And now for a fun fact. A refrigerator, or freezer, is nothing more than a fancy cooler with a small heat pump. Side note, here in the US, we use the term heat pump to generally mean a reversible air conditioning system, which was how I used it earlier when I talked about how they'd be instrumental in our fight against climate change. But more correctly, any refrigeration system is a heat pump at its core. The job of a heat pump is to concentrate and relocate heat energy by means of a refrigerant. Whether we use that to heat a space or cool a space is entirely up to us. Anyway, the walls of the fridge are insulated just like the cooler, and their job is to keep the heat energy from the room it's in from getting inside and warming up your foodstuffs. Now, it can't keep heat out forever, it can only slow the rate of heat transfer. So we need a heat pump to run periodically so we can force it back out. That's the job of the compressor. Well, technically, the compressor is only one part of the heat pump, but it is the pump part. When you hear someone talk about the compressor in a refrigerator, this is the component that makes the buzzy sound and makes the cool happen. The compressor is compressing the gaseous refrigerant, forcing it into a confined, high-pressure heat exchanger known as the condenser, where it can release its excess heat and condense into a liquid as it does so. All so that, after passing through a metering device, the now liquid refrigerant may then enter the refrigerated space, where it will boil away thanks to the relief of this new low-pressure heat exchanger called the evaporator, scavenging heat as it does so from inside the space and making it colder. But I said we wouldn't focus too much on the mechanics, and here I go talking about it again, so let's move on. One thing I'd like to highlight here is that unless you load it up with a bunch of warm food, the only thing your fridge is battling is energy from the room it's in getting inside. Once it's down to temperature, that is a relative constant. A lot of people will suggest that you avoid an empty fridge because a larger thermal mass inside it will make it run less frequently. This is only kind of true. The amount of energy entering it does not change with the amount of food that's inside it, which means it doesn't impact how much it needs to work. What does actually change is how quickly energy entering it from its exterior will cause the inside temperature to rise. Without a lot of thermal mass, the same energy input causes a faster temperature gain, so the compressor might need to run more frequently. But that also means it won't need to run as long to get back down to temperature. Again, less thermal mass means the same change in energy causes a greater or faster change in temperature. What you're really avoiding with a fuller fridge is short cycling, where the compressor comes on more frequently in shorter bursts, which could in theory lessen the life of your refrigerator and may slightly impact its energy efficiency. But it's probably not as big of a deal as you think. So if we want to increase the energy efficiency of a refrigerator, we have exactly two possible courses of action. We can design a more efficient heat pump, or we can minimize environmental heat intrusion through better insulation design and application. And here's an important fact. There aren't that many gains we can find in the heat pump part. Yet, anyway. We've gotten pretty good at this whole refrigeration thing. Even as we've discovered that the refrigerants we used to use are not fantastic for many reasons, thanks Thomas Midgley Jr., we've adapted with new chemicals and really, we've got that part pretty much down. But there's a lot we can do with the design part, and now we are back to the humble chest freezer. These unassuming white basement boxes of last year's turkey and grandma's popsicles are really quite remarkable. Why? Because of their bonkers energy efficiency. These are as close as you can get to a literal cooler with a heat pump. Because that's just about what they are. It's a box with a lid with thick insulated walls, and a small heat pump works to periodically move heat from inside the box to outside the box, keeping its temperature sub-zero cold and regulated with the help of a thermostat. Now, if you go shopping online for a chest freezer and you take a look at their energy usage, you might soon find that, well, that's almost insignificant. And, well, compared to a lot of things in your home, you'd be right. I plugged this little chest freezer into a kilowatt to see for myself and, well, I was stunned at how efficient this is. When running, it only consumes about 100 watts of power, and over a period of 3 days, it consumed just 600 watt-hours per day. Considering average US electricity prices, this means that the operating cost of this freezer is just over $2 per month. That's nothing. I mean, seriously, if you put just one frozen pizza in this freezer, that pizza would cost more than an entire month's worth of electricity supply for its preservation. You could put hundreds of dollars of food in here and preserve all of it for mere pennies a day. Its absolutely thrifty energy consumption means that you could power this easily from the output of just one commercial solar panel. A 250-watt panel getting an average of just 3 hours of sun per day would take care of it no problem. Assuming there's some storage involved, of course. And this particular freezer isn't even that efficient. All things considered, it's actually quite lousy. Considering this model with nearly double its capacity uses pretty much an identical amount of energy, this actually starts to seem kinda bad. But I mean, it's still just $2. That's impressive. So what makes this so efficient? Well, a couple of things. First, this is a manual defrost freezer, meaning it will build up frost over time and needs periodic downtime to melt that away. But it doesn't need that to occur all that often because of the second fact that makes it so efficient. Its door is on the top, like a cooler. Consider what happens when you open the lid. The air inside the freezer is very, very cold, which means it's very dense. You've undoubtedly heard before that warm air rises and cold air sinks. Well, if this is full of cold air, and there are walls on 4 sides holding it all in, opening the lid does almost nothing. There's a sharp temperature gradient maintained just by the boundary between the warm air in the room and the dense cold air held in the freezer. If the door is on the front, as it is for an upright freezer or any refrigerator, every time you open it up, the cold air inside of it falls right out. You've probably seen this happen on a humid day when opening your freezer. The clouds of steam you see falling down are the result of the cold air in the freezer mixing with the warm air in the room, pulling the water vapor out of the air and making it visible as it falls to the floor. It literally is a cloud in your kitchen. And, of course, if all that cold air has fallen out, it must have been replaced by the warmer, less dense air in the room. You'll likely have noticed before that when you close the door to your freezer, the door seems to get sucked in after you close it, making it hard to reopen immediately. This happens because the warm air that entered it as you browsed your food Netflix is now sealed in the freezer, so it cools rapidly thanks to all the cold stuff inside, and in effect shrinks. This creates a dramatic pressure imbalance between the inside and outside, making it hard to open the door again until the pressure equalizes. And of course, the freezer will eventually need to work to remove that added heat energy introduced by this warm air. This hardly happens at all with a chest freezer. There is some suction force when you close the lid, but it's very weak and very brief, almost unnoticeable. That's because hardly any new air makes it in thanks to the literal tub full of cold, dense air. It can't just spill out. Want proof? If you get a leaf blower and shove a bunch of the room's air in there with hurricane force, now when you close the lid there is noticeable suction, and it lasts quite a while. So there you go, proof right there that the walls of the freezer hold the cold air in place. Seriously, if you've got a chest freezer and a leaf blower, try this at home, it's fun. And going back to the defrosting part, the fact that the cold, dense air stays inside helps minimize the need to defrost it. In this freezer, and many like it, the evaporator, which is the part that gets cold, is embedded in the walls of the freezer. That means the walls get very, very cold, and moisture in the air condenses on them and subsequently freezes. Over time, this causes ice to build up. But since the amount of ambient air that enters the cooled space with each opening is quite small, that buildup is relatively slow. Here's the thing though. Chest freezers, as neat as they obviously are not the easiest things to live with. While they have most certainly been endorsed by the Royal Society for putting things on top of other things, the fact of the matter is, filling these up with food means burying some of your other food in food. If accessibility is at all important to you, this design frankly sucks. I am very happy to have a chest freezer full of food right about now, but getting to the food on the bottom involves a fair bit of rummaging. And of course, that means rummaging through ice-cold food. You might want to consider investing in a pair of warm gloves should you decide to purchase a chest freezer. And of course, if you want a freezer with a larger capacity to hold food, well, in the land of chest freezers, that means you need more floor space. You can't simply make the chest deeper. Well, okay, you could, but good luck with that. So instead, it must be wider. If, on the other hand, you have an upright freezer, you can make the freezer taller, granting you more interior volume with the same floor space. And thus, we've circled back to the introduction. Chest freezers are undoubtedly the best design if energy efficiency is your main goal. But to achieve that goal, you must make sacrifices in convenience. And I think it's okay to be unwilling to make those sacrifices. But that doesn't mean we shouldn't think about them. I'd argue, as is the case for most things in life, there's a sweet spot to be found. That might be different from person to person, but I think it's a little too easy to be swept up by what's in and popular without thinking about whether that actually fits your needs. And refrigerators more broadly are just one of many places where we can see this in action. Let's go shopping for a fridge, shall we? We're going to take a look at various models and compare how much energy they use. You'll soon find that the design of the fridge has a significant impact on its energy consumption. And let's start with a weirdly counterintuitive fact. Freezers tend to use less energy than a refrigerator of the same size. Let's look at this big 15 cubic foot chest freezer. This huge freezer still manages to use less than a kilowatt hour per day. And it's a freezer. It has to keep its insides at near 0 degrees Fahrenheit or minus 17 Celsius. All of its insides. So its entire inside space may be fighting a 60 or 70 degree temperature difference. Likely more. Now let's look at a basic kitchen refrigerator. This one is about the same size as our chest freezer, just a little smaller. Your intuition might tell you that this should consume less energy. After all, the bulk of its insides are at a warmer temperature than a freezer. It shouldn't need to work as hard. And yet, it actually uses more energy. Not a lot more, but still more. What's going on? Well, there are 3 basic differences here. The use of one heat pump for 2 temperature zones, the design and weaknesses of its thermal barriers, and whether or not the device has an automatic defrost function. Now, spoiler alert, that last bit is less important than I thought it was going to be. It does still matter a little bit, but let's set it aside for now and start with the first part. The vast majority of residential refrigerators have only one heat pump. Really, what they are is a small freezer with an additional compartment that leaches off the freezer a little bit to get some cold air. You'll no doubt have noticed the whirring of a fan at some point, and this is what that's for. Or at least one of them. There may very well be multiple fans in your fridge's design. And of course, there are exceptions. Feel free to comment about them. It boosts engagement. This may not seem super important. After all, it's a pretty clever use of resources. Just oversize the heat pump for the freezer a little bit, and use part of its efforts for the fridge. But you'd be surprised how much of a difference it makes where you put the freezer. I mean, just compare these 2 fridge models. Same overall size, same manufacturer, and no difference in features, other than the fact that the position of the freezer and refrigerator is reversed. The freezer on bottom model uses about 20% more energy. That's significant. Now, I've been trying to get a firm answer as to why this is. At some point in the past, I had heard, and it makes intuitive sense, that because cold air tends to sink as it's denser, it takes less added effort to move the output from the freezer into the refrigerator if the freezer is on the top. Just sort of let the denser air fall down into the fridge compartment. Whereas if the freezer is on the bottom, or even on the side, you need to actively move air around to achieve the same results. And that might take more energy. But I couldn't find a definitive answer as to whether or not this is the precise case. Regardless of the exact root cause, conventional freezer on top models tend to be the most energy efficient design. Just take a look at this list of most efficient refrigerators on the Energy Star website. The vast majority are models with the freezer on top. There are exceptions to be found, but not many. And freezer placement is only one part of the equation. One of the more surprising things I found was that turning the freezer into a slide-out drawer causes another 17% increase in energy consumption. That's honestly really interesting to me. I wouldn't think that would make much of a difference, but apparently it does. Uh-oh, confounding variable alert. The bottom drawer model has an ice maker, whereas the swing-out door one does not. That will cause an increase in energy consumption so long as it's making ice, since it needs to remove energy from the water it's introducing to itself. Without knowing the specifics of how the energy guides account for that, it's not necessarily fair to assume the slidey drawery bit is what's making it work harder. So, okay, specifics unclear. But speaking of ice, another significant factor in a refrigerator's energy consumption is whether or not it has an indoor ice dispenser. Because, and here's a fun fact if you've never realized this before, That means it has a hole in its door. Yeah, sure, it probably has a flap or something to seal the hole when it's not vomiting ice chunks into your glass at an entirely unpredictable rate, but a thin plastic flap does not a good thermal barrier make. That would be a wonderful place for ambient energy to find its way inside. Also, how does that even work with a bottom freezer French door fridge? Is there like an entire, like a whole ice maker inside the door? Well, anyway, this is such an important factor in the energy consumption of a refrigerator that it's specifically noted on the energy guide whether or not the particular model has it. It's kind of a big deal. But on the other hand, is it really? I mean, let's look at the energy guide again. Sure, there's a big swing from the low end to the high end, but honestly, even the least energy efficient refrigerators out there still cost less than $8 a month to run. It gets a little worse with bigger models, but if you happen to have an electric water heater, well, in comparison to that, even the worst refrigerator is peanuts. However, we all have refrigerators. Lots of us have more than one. And that means that while there's little noticeable difference to our individual pockets when it comes to our electric bills, well, 100 million refrigerators using an additional 250 kilowatt hours per year means that we're using another 25 billion kilowatt hours. You can make whatever comparisons you'd like with that figure, but the one I'll make right now is that if every single US citizen who drives to work drove an electric car, so that's 128 million cars, based on a rather conservative 3 miles per kilowatt hour, every single commuter could drive 585 miles with that extra energy, or about 3 entire weeks of commuting. Small gains, when applied across the board, add up a lot faster than you'd think. Which is of course why we have regulations regarding how much energy appliances can consume, and why utilities offer rebates for purchasing more energy-efficient appliances. But before we get too far down that particular opinionated path, let me just repeat that I think it's okay for us to accept some losses in efficiency if it improves our lives. The question we need to ask ourselves is how far we are willing to take that. As is the case for nearly everything in this world, well, there's a happy medium. You might be wondering why chest refrigerators don't exist. Well, they almost do. A lot of people living off the grid will convert chest freezers into chest refrigerators by modifying their thermostats. I mean, if it can cool down to 0 degrees, well, surely it can just stop at 35 and be a wildly efficient refrigerator. And it can. But the people who make this modification do it because to them, energy consumption is the single greatest concern. They're willing to make the sacrifices necessary to achieve that end. And more power to them. But we don't all need to go to that extreme. Then again, it's possible to end up on the other extreme. The most popular style of refrigerators these days, and by that I mean the most desirable, whatever that means, seems to be the French door bottom freezer models. And, well, they're kinda the worst design for energy efficiency. At least the way manufacturers build them today. I have no reason to think their efficiency couldn't be improved. Some manufacturers, like Samsung, use separate evaporators for the freezer and fridge, meaning that while there is still only one compressor and condenser, each compartment is in effect cooled separately, which might help reduce energy consumption. And in fact, one of these French door bottom freezer models has made it on the Energy Star list. But what does it say that the model we all seem to lust for is also the most expensive to run? I'm not here to pass judgment, no matter how much I'd like to, because I think it's okay for us to have different priorities. But I am here to suggest that we think about them a little more. The entire reason we have energy guides in the first place is to encourage consumers to make the more frugal choice, both for their wallet and for the environment. If there's anything I'd suggest we do change, it would be that we make focusing on that label just a little bit cooler. Thanks for watching. Yes, it's still there, and I hope that you learned something interesting with this video, and that it gets you thinking about your personal sacrifices and priorities. Again, I'm not here to be judgy. I hope you didn't think that's what I wanted to accomplish. I really just want to get your mind gears turning. It can be easy to go above and beyond our needs every day, and I am guilty of that in many respects. But now and again, I think it's worth considering reeling that back a bit. Oh, and the thing about defrosting. So, this is probably the main reason conventional refrigerators use more power than a standalone freezer. Since nobody wants to deal with defrosting their refrigerators anymore, we design them with means to eliminate the ice on the evaporator. Usually this is done by running the fans while it's not cooling and/or using heating elements to melt the ice. There's no free lunch, so that takes more energy. But also, it's not anywhere near as big of a deal as I thought. It turns out that we have a direct comparison between an upright freezer without auto-defrost and one which does have auto-defrost. And it's not as dramatic a difference as I thought it would be. Indeed, the freezer still manages to use less power than most refrigerators of a similar size. So that's why I left it for here at the end. I would never suggest anyone look for a manual defrost kitchen refrigerator, if they even exist, because I would not wish that burden on anyone. And now, the bloopers. I believe you all have a right to know that I have been wearing Simpsons Christmas pajamas during the filming of this video. It's a cooler. Overheat the size pump. I almost said that. I didn't, but then it got in my brain, and then I couldn't keep going. The height of it falls right out. There was a weird noise on the F there. Yeah, that sentence is... Ooh, why did I write it like that? I'll try to rework it on the fly, which always goes great. Nope, I said enter, not enter, and gotta start over. Most desirable. I was saying desired, and then I read what the real word was, and then I realized, abort!